Welcome back to Respiratory 121, and this week we'll follow the gas itself from where it's made all the way to the safe supply at the bedside. And I want to start with something that puzzles a lot of students. A full oxygen e-cylinder, that small one that we would grab and transport, reads somewhere around 2200 psi. And that's a huge amount of pressure, but your hospital doesn't store its main oxygen supply that way. It keeps oxygen as a liquid, an extremely cold liquid, two completely different ways of storing it. So let's talk about the gases themselves. Start with air around you right now. It's about 78% nitrogen and 21% oxygen. Keep that fact handy because we're going to come back to that in just a minute. So now, oxygen, here's something people get wrong all the time. Oxygen is not flammable. It doesn't burn, but oxygen does strongly support combustion. That means anything already burning burns faster and hotter with more oxygen around it. So we're not saying oxygen is fuel. We're saying it feeds a fire that drives a lot of our safety rules that we'll discuss later on. Medical air is exactly what it sounds like: atmospheric air, and that's filtered and compressed to medical standard. So carbon dioxide shows up mostly for calibration and a few diagnostic uses. But then you have helium, which is a very low density gas, and we give it mixed with oxygen and a mixture we call heliox. And for select kinds of airways obstructions, we give that for. Now, notice something about the two, though. Carbon dioxide and helium don't support combustion, but they can displace oxygen. In a closed space, they can push oxygen out, and that's a suffocation risk. So, doesn't support combustion doesn't mean not harmless. Two more gases I want to cover. Nitric oxide is an inhaled gas that dilates blood vessels in the lungs, and that's called a pulmonary vasodilator. It's opening the radius of the vessels. And nitrous oxide, N2O, is a weak anesthetic used for analgesia and sedation. It can be used for pain relief and calming. So, where does the gas come from? So, remember from our Dalton's law, right? We talked about partial pressure. So remember that 78 and 21? So oxygen's around 21%. Bulk oxygen starts as ordinary atmospheric air, and that air gets cooled until it turns into a liquid. Then it slowly warmed back up. Different gases boil off at different temperatures, so you can separate them out at one at a time, and that process is called fractional distillation, and is the main way bulk oxygen is produced. Good to know that. So then you have medical air, and that's a little simpler. So you take atmospheric air and you filter it and you compress it and then you dry it, and that's it. Now, here's a part that this whole video is built toward. Medical gas reaches us in four ways. So first, compressed gas. This gas is squeezed into a cylinder at a high pressure, and but it stays a gas the whole time. You're just compressing it, and we call that a non-liquefied compressed gas. So that, think of that as an oxygen e-cylinder, the little tanks that you see people carrying around or at the hospital. Some gases, if you compress them enough at room temperature, actually turn into a liquid inside the cylinder. So the cylinder holds liquid at the bottom with vapor sitting on top. And then third, we have cryogenic liquid. And that's a gas kept liquid by keeping it extremely cold inside an insulated system. That big bulk liquid oxygen tank outside the hospital, that's a cryogenic liquid. And fourth, generated gas. An oxygen concentrator is a generated source. It pulls in room air and concentrates the oxygen. So the how it's stored can tell you or help you decide what the pressure gauge actually means and what it's telling you as far as reserve. Okay, so take a non-liquefied compressed gas. Remember our oxygen E cylinder? Everything inside it is a gas. So as you see it, the pressure falls in a steady and predictable way. Half the pressure, roughly half the contents are gone inside of that tank. For oxygen cylinders, the gauge pressure gives you a useful estimate of the remaining contents. And in class, we'll actually use pressure cylinder to calculate volume and duration. Now, take a liquefied gas. A gas leaves the cylinder, more liquid evaporates and replaces it. So the pressure can stay fairly steady as long as the liquid remains. The gauge might read almost the same when the cylinder is nearly full and when it's nearly empty. Then the liquid runs out and the pressure drops fast. So here's your stop and think question, and it's the one on the slide. Why can two containers with simple pressure readings hold different usable supplies? And that brings it back to our opening question. That E cylinder you grab for that transport stores oxygen as a compressed gas. It's portable, simple, and the gauge tells you what you have. The hospital bulk supply stores oxygen as a cryogenic liquid because liquid oxygen packs an enormous amount of gas into a small space. The storage method is not a minor equipment detail. So in the next video, we take the next safety step, verifying that you have the correct cylinder and the correct connection before any of the gas moves toward a patient.